Alright, so we're going to be talking about using absolute values and transforming them. Now we've dealt with absolute value and their transformations when we first spoke about parent functions. Now we're going to go into a little bit more depth and seeing what sort of graphs and transformations we can make with a greater sense of accuracy. So recall that the absolute value parent function is f of x equals the absolute value of x. And this is going to create a V shape, and we can attribute that V shape from the property of absolute value that makes negative numbers positive. So for instance, we have a point here to the right of, let's say, 2, 2. And I'm going to have another point mirrored on the left side, reflected over the y-axis, of negative 2, 2. And the reason for that is, if I were to substitute in 2 for x, so I'm going to have f of 2 is equal to the absolute value of 2, then f of 2 is simply going to equal 2. And that's how we get this point on the right. Now, when I substitute the negative 2 for x, so the absolute value of negative 2, then f of negative 2 is equal to, well, positive 2. Hence, an x value of negative 2 and a y value of 2. And that's why we get that mirroring effect, is because every time we substitute a negative, we end up getting a positive. And so when we plot all these points, we get our absolute value function. And another thing that's really interesting about this is if we just bisect this into two parts, a right part and a left part, kind of like, well, if I just kind of cut it down the y-axis like so, and I were to look at this part on the right, this branch, then I would notice that this would match the linear parent function. If you'll notice, this has a slope of 1, over 1, up 1, over 1, up 1. And it has a y-intercept. It'll cross here at 0, 0. So it has a y-intercept of 0. Thus, we would say that this right branch has an equation of y equals x, the same as a line or the linear parent function. And likewise, if we look at the left side, it's going to if we look at the slope, we go down 1 over 1, down 1 over 1. And so it's going to have a slope of negative 1, but it has the same y-intercept. So thus, on the left side, it could be matched up to the reflected linear parent function. So we add a negative in front of the x. There's that slope of negative 1 in front of the x, and a y-intercept of 0. So that's a unique thing that we can use to our advantage when it comes to graphing absolute value. It'll make our lives easier. As opposed to having to plot every single point, we can use these linear properties to make it a lot easier as to plugging in and plotting. One other property is of the absolute value function is this point here where the two branches meet. This is known as the vertex. And the vertex is always located on the origin, on the parent function. So you'll see that terminology used a lot, the vertex. So just be aware of what that is. Okay, so what two equations can be used to graph this absolute value function? In other words, we're going to look for a couple lines, one that will match the right side and one that will match the left side of this absolute value function. So since we're going to have two different lines here, let's go ahead and define what we're going to need. We're going to need a slope, and there's going to be two slopes, so I'm going to have a sub 1 and a sub 2. I'm also going to need a y-intercept for each. So b sub 1 for the y-intercept for the first one, and b sub 2 for the second one. Okay, so let's start off with the first line, which would be, I'm going to call the right side. If I look at the slope, I would just pick 2 points. So let's say one here at the vertex and one up here on the origin. If I were to count this out, it looks like I'm going to the right 2 and I'm going up 1. And so since our slope is y over x, or the change of y over change of x, aka delta y over delta x, that's going to be 1 over 2. And for our y-intercept on this first line, I can see that it crosses at the origin. So that means it's going to be at 0, 0. So therefore my y-intercept, or my b value for my y-intercept, will be in fact 0. Now let's work on the second line. I would pick 2 points, so I'm going to pick 1 point here. This looks like a good point, a couple whole numbers here. Looks like -4, 0. And from here I'm going to go to the vertex. So I'm going to go down 1, so -1, and then to the right 2. So therefore my slope here is -1/2. Okay, so when getting the y-intercept on this one, see, it doesn't cross because it's not really a line, it's a ray. So we'll have to extend this slope out and see where in fact it's going to cross on the y-axis. So I'm just going to extend out starting from the vertex using the slope. So I'm going to go down 1 and over 2. And it looks like it's going to cross here. So again, if we were to extend this out like so, we would see that it would cross at -2. So for my second y-intercept, I'm going to put -2. So my first line, y equals slope of 1/2 x. Since my y-intercept is 0, I'm going to stop there. And then for my second line, y equals -1/2 x. And then my y-intercept is -2, so I'll put -2. So there are my two equations, linear, meaning they make a line, and that would fall in place with the absolute value function. Okay, now recall the general function. Now this is different from the parent function. The general function is just how all the different pieces work as far as our transformations are concerned. We have our a value, which is deals with our reflection when a is less than 0, when it's a negative, and deals with our vertical compressions and our vertical stretches. So that always is in front. Then we have our horizontal shift, and that tells us how far we shift to the left or to the right. And remember, because of the minus sign, it's going to work backwards. So if we have a -2, it's going to go right 2, and if we have, let's say, a +3, then it's going to move to the left 3. And then our vertical shift is k, and that's always at the end, and that's just going to be our simple shift up and down, and it's direct. So +4 means just going up 4. So let's use this combination of being able to view this as lines, both branches as lines, and how that works as far as transforming a absolute value function. So we're going to graph the function f of x equals -1/2 x plus 2, absolute value of x plus 2 plus 3. Now I've put the absolute value parent function on here as a reference for when we start graphing this child function. So the first place we want to start when dealing with the graphing the child function is knowing, is dealing with the vertical stretch and the vertical shrink and the reflection. So in other words, we want to deal with the A value first. So recall that each branch is a line with a slope of, well, this one is a slope of 1 and the left side is a slope of -1. So because I have a value of -1/2, it tells me that it's going to be vertically compressed, like so. It's going to be, squished this way, so it's going to be wider as a result when you squish something up and down, and it's going to be reflected. So the way that's going to look like is I'm going to essentially have a slope of 1/2. Okay, so normally if it was just 1/2, we would start at the origin here, and then we'd say, okay, well, I'm going to go over 2 and then up 1, and then over 2 and then up 1, and I would start plotting points like this, and then I'd go in the other direction like this, so over 2, up 1, over 2, up 1. But it's reflected, so that means we're going to have to go down 1 and over 2. So let's do that. Okay, so I'm going to go over 2, and because it's negative, it's going to go down 1. So here's my first point. Actually, my first point is going to be at the vertex. So my next point is going to be here. And then I'm going to go over 2, and then down 1, over 2, down 1. Okay, so 3 points plus the vertex is enough to get us started in that direction. And let's see, that's going to put us about like this. Okay, so I'm just going to start off. I'm graphing this kind of intermediate graph, and then we'll do the other transformations. So now I'm going to go the other side. So this case, we're going to go. I'm just going to kind of work it backwards. I'm going to go left 2, down 1, left 2, down 1, left 2, down 1. And remember, it should look like it's just reflected over the y-axis if you did that correctly. And that's how you can tell if you did that. Okay, so there it is. We can see that it's wider and it's reflected. Now the next thing we want to do is we want to deal with the horizontal shift of it's just +2, so that means we're going to go to the left 2, and then we're going to go up 3. A good place to start is with the vertex. The vertex comes in very useful at this stage when you start doing your shifts or translations. So my vertex is originally here at the origin. So +2 tells me I'm going to go left 2, and then I'm going to go up 1, 2, 3. So here is my vertex. And now I'm just going to plot the points like I did with this intermediate graph. So that means I'm going to go left 2, down 1. So left 2, down 1, left 2, down 1, left 2, down 1. Okay, so we treat it like a line that has a slope of -1/2. And so it's going to, this branch is going to be like this. Make that big and bold so there's no question as to what that is. And then I'm going to go on the other side here and do the same. So I'm going to work it backwards. Left 2, down 1, left 2, down 1, left 2, down 1. So you have the vertex, and then 3 other points on either side will be what we're looking for. That will be a good amount to use. You can always do more. I prefer if you didn't do less, though. And so it's going to look like that. Okay. As always, don't forget your arrows. Let's see. So there's no doubt as to what my final graph is. There it is. Okay, so I've went ahead and vertically compressed it, and we transformed it to the left and up, and it's reflected. So there we go. So let's kind of run down the what we did there. So what we did with that transformation, as far as the absolute value function, works with any transformations with any function. So we can put this in a general form. So it could be, let's say, a square root function, or a quadratic, or a cubic. And the general form for any of these is y equals a times f of x, or f of x minus h plus k. So this generically works with any function, and we can get those transformations with the same a, h, and k. Now the order we want to do this in is, first, in step one, we want to take care of any stretch or shrink. Okay, and that also is going to include, well, we want to take care of any stretch or shrink, and then we're going to want to deal with the reflection. Okay, now you can actually stretch and shrink and reflect in a single step, but if you are not quite comfortable with that, which is fine, then you can stretch and shrink it, then reflect, and then finally we will in step 3 we will translate it horizontally h and vertically k units respectively. Okay. So this works for everything, any sort of function whatsoever. Even if it's not a function, a clearly defined function that we know of, that we can set an equation to, so or a single equation to. So for example, here's a graph where y equals f of x, and we want to we're going to consider this some arbitrary function that we don't have a name for, and this is the parent function of that function, and what we want to do is transform it. So here I have -1/2, which means I'm going to reflect it and vertically compress it. -1 here tells me we're going to take whatever this function is and shift it to the right one, and then we're going to shift it up 2. So when you're tackling something that is not a familiar function, it's best to take some points and build a table like what we have here. So I have a series of points like -3, 3, 0, 0, and 3, -6. I'm going to jot those points down in our table. I'm going to start with -3, -3, and then 0, 0, and finally 3, -6. Okay, now what I'm going to do is I'm going to start doing my transformation, but on the points, and then I'm going to build a new table here, or I'll have some new values in my table, and I'm going to plot those points and then create my graph. It'll be a lot easier for us to do that approach. So first we want to take care of any vertical stretch, shrink, or reflection. I'm going to first deal with vertical stretch or vertical shrink, and then we'll deal with the reflection. So here, let's take a look at what we have on the left. So since I have a 1/2 here, that means we're going to vertically compress it. Now remember, it's a vertical compression. Keyword vertical, meaning that we're only affecting the vertical or the y values. It's not horizontal. Horizontal deals with the x, vertical deals with the y. So therefore, the values that we're going to be applying this to is going to be values like on the first point, -3, and then the 0, and then the -6 here. And we're all going to scale those by a factor of 1/2, or multiply them by 1/2. So therefore, when I do this, I'm going to say, all right, well, this point is now going to be -3, and then I'm going to multiply this -3 by 1/2, and that's going to become -1.5. Okay, and so over here on my table, I'm going to cross this out, this -3, and I'm going to put -1.5. So I'm just dealing with the vertical compression, not dealing with reflection yet. And then 0. Well, when I multiply this by 1/2, it's still going to be 0. And then so this is going to remain the same. It's still going to be 0. I'm going to cross it out though and write 0 just so I can keep track of where I am. And then this point is going to be 3, and then 1/2 of -6 is -3. So over here I'm going to put -3. Now, since this is a -1/2, I can go ahead and make all of these, well, change the signs on all of them. So -1.5 becomes +1.5, and -3 becomes +3. So I'm going to go ahead and make that reflection change. All right, now that we've dealt with the vertical shrink or compression, we can now deal with the horizontal and vertical shift. Let's deal with the horizontal shift first. So the horizontal shift deals with our x values, left and right, and x goes left and right. And since we have we're saying -1, that means we're going to shift it to the left one. So now this point goes from -3, we shift it left one is going to be -4. Okay, so now we're at -4 and then 1.5. So over here I'm going to cross this out and just make it, oh well, that's -4. And over here I'm going to shift this left one, so this becomes -1 and 0. So this is -1, and this becomes 2. So that's going to be 2, 3. All right. Finally, we're going to deal with our vertical, and that's going to be +2. So that means we're just going to add 2 to the y, since y is vertical, and we're just dealing with vertical shift here. So the the 1.5 we're going to shift up 2, so that's going to become just 0.5, or 1/2, so we have -4.5. So over here I'm going to cross this out and put oh, let me correct that, my mistake. We are adding 2, so that's actually going to be 3.5. I was subtracting for some reason. So that's going to be 3.5. So let me put 3.5. So our next point, we're going to shift this up 2, so that's going to become -1, 2. So this becomes 2. And this point here, we shifted it, and that's going to become 5. So 2, 3, 2, 5. And let me correct this. I said 2, and I wrote 2, except there I wrote 3. Okay, cool. All right, so I have my final order pairs for this new function, which is going to be -4, 3.5, -1, 2, and then to 5. Okay. So let's go ahead and plot those. All right, so first point, -4, 1, 2, 3, 4, and 3.5, 1, 2, 3. Okay. -1 and 0. So that's going to put us here. And then to 5. 2, 1, 2, 3, 4, and 5. Okay. Now we just draw lines here using whatever straight edge we have available to us, like so, and like so. So there we have it. We went ahead and successfully transformed a function that we have no equation for by using a series of points and then applying the transformations one at a time. So that is absolute values and transformations. Thank you very much.